left are small ovals representing the size range of blimps, specifically the C-class blimps from 1918 and the N-class blimps from 1962. On the right, the ovals represent rigid airship sizes, specifically the LZ-18 from 1913 and the Hindenburg from 1935. So the largest blimps are just about as big as the smallest rigid airships. So why don't they make blimps bigger? Is there a reason they are the smallest type of airship? Is it an engineering reason? Yes. That reason is stress. Not the type of stress you get when you haven't done your homework and it's time to turn it in, but mechanical stress. This is Bob. Notice how happy he is. When we apply a force to Bob, he gets unhappy. Take the forces away and he is happy again. This unhappiness is what we engineers call stress. And just like people, if you put too much stress on Bob, he will crack and break. The basic definition of stress is the force divided by the area. So the larger cube on the left will take more force to break than the smaller cube, assuming they are both solid and provided they are the same material, because different materials can handle different amounts of stress. However, airships are not solid cubes. Here we have a blimp and a rigid airship. In a blimp, most of the stress is carried by the balloon, but the rigid has a metal frame that carries the load. Now this is a balloon. Inside there's air. It has pressure and it pushes outward. If we look at the cross section of the balloon, we see that the balloon has a radius and a thickness. Using these measurements and a lot of advanced calculus that I'm not going to show right now, we get the equation that stress equals the pressure times the radius divided by double the thickness. The radius of a blimp is usually around 1/16 to 1/64 of an inch. Wait, that's actually the thickness of the fabric. The radius of a C-class blimp is 456 inches. The maximum operating pressure of a blimp is usually 10 inches of water, which is about 0.36 psi. Altogether, that gives us a stress of about 1,313.28 psi if you assume thick fabric. If you use thin fabric, it'll be higher. Most woods can only handle up to 5,000 psi of stress, and most fabrics I have tested in the past can handle between 2,500 to 5,000 psi. So this blimp will function reliably. After all, it is a historic design that worked fine. If we change the numbers for an N-class blimp, the radius changes to 810.5 inches. We'll assume they use thick fabric for this blimp too. This makes the stress up to 2,334.24 psi. This is almost the limit of standard fabrics. Now, if you were to use amazing fabrics that were super duper strong, you would still run into another problem. As you make the blimp bigger, the gondola gets heavier and the balloon gets longer. With most of the weight concentrated in the middle, but all the lift spread out over the entire balloon, eventually the blimp starts to sag in the middle. Now, some people don't mind sagging balloons at first, but the sagging also raises the pressure, and historically most sagging balloons were fine at takeoff but did not survive the test flights and fell out of the sky. This is why you never hear about ginormous blimps. The physics just doesn't work out if you make them that big. Thank you for watching to the end. Please remember to like, comment, and subscribe, and if you want to support the building of airships, there are links in the description to help you know how to do that. Thank you.